So I thought it'd be useful to talk about what you need to do for this programming assignment. So I'll talk about the concepts and the mathematics required, and then you should just be able to take what I've described and write some code and do it. Maybe a little bit more math will be needed. So for this programming assignment, you're going to be dealing with this simulation. So what is a simulation? You have n coin flips. N is the length of the sequence of Bernoulli trials. A Bernoulli trial is just like a coin flip, biased coin flip, right? So we have n of these coins that are flipped. And the result of the simulation of flipping n coins is the number of heads that come up, right? So we flip a certain number of coins, we flip n coins. They have bias p. This is the probability of each coin coming up heads. And we're interested in the number of heads that come up after we run this experiment. Okay, so how do we write this? How do we formalize this mathematically? So we can write this as a random variable x. This is the sum over Bernoulli random variables xi. And now we want to make computations about this random variable x, right? So the distribution of x is going to look something like this. So the probability of getting, let's say we flip 10 coins, then the probability of getting, let's say p is 0.5. So it's an unbiased coin. So mu here is 0.5 times 10 equals 5. So the mean of this distribution is going to be at 5. So we would expect something close to 5 coins to come up heads if we flip 10 and they're unbiased coins. 4, 1, 2, 4. So the probability of 0 coming up is low. It's going to go up all the way to 5, and then it's going to decrease. And the most we can get is 10, right? Because we flip 10 coins, at most 10 can come up heads. So the distribution is going to look like this. And what you want to compute is, let's say L equals 6 and U equals 8. So this is 6 and 8 here. You want to compute the probability that this many coins in this range come up heads. So this is the number of heads on the x-axis, and this is the probability of getting this number of heads. So this is the probability of getting this number of heads. And so you want to compute the sum over these probabilities. So that's the goal of this assignment. So we're going to compute it in 3 different ways. And this is given by the variable t. T is passed in on the command line, and that will determine which way you're using to approximate or exactly compute this number. So we'll start off with the exact case. So the exact case, well, this is a Bernoulli distribution. So we know how to compute. So we have x parameterized by, so the probability x takes on a particular k. So k is the number of heads, parameterized by n and p is n choose k, p to the k, 1 minus p, minus k. So you know this. This is just a Bernoulli distribution. Or this is the binomial distribution. If it were one flip, it would be the Bernoulli distribution, right? So this is for a particular case. So if you want to calculate the probability x is between the lower and upper bounds, you can just sum over each k between L and U. So we can just, if we want to calculate the probability of getting 6, 7, or 8 heads, we can compute this as the probability of getting 6 heads plus the probability of getting 7 heads plus the probability of getting 8 heads, since these events are disjoint, right? So this is just the sum k between L and U, p x equals k. And you can just expand the binomial distribution and get n choose k. Okay. So this is the exact case. So this is how you would compute. This is how you would compute the probability of getting within this range of heads exactly. So in the next cases, so we're going to compute an upper bound. So we're going to say that we're going to compute an approximation that says the probability is at most something, and that's Chebyshev. And in the second case, we're going to sample. We're going to generate samples from this distribution, and we're going to see out of how many of these samples come up between 6 and 8. So let's take the sampling case. So we want to generate samples. So we have n. We want to generate samples of x, right? So let's call these. Let's use superscript notation. So like x1, x2, xm. We're using a different m. So this m is the number of samples. So each sample is a sampling from this distribution here. So we take n coins, we flip them, we count the number of heads, and that gives us one sample here. So for this case, the values for each of these samples might be 6, 7, something, 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 3, right? So these are going to be between 0 and 10 inclusive. And we're going to approximate the probability that x, a sample from x, lands in this interval empirically by counting the proportion of these samples that happen to be in the interval. So we're going to run, each simulation we run involves flipping n coins, here, in this case 10 coins, and then calculating the number of heads that come up. So we can do random flipping in programming. There's a random function. Every language imaginable has a random function. So in this case, let's say m, let's be concrete, let's say m equals 7. So let's say the values are 6, 7, 2, 4, 3, 9, 10, right? 2, 4, 6, 7. So if we wanted to approximate based on a sample of 7, the probability that x is in the range 6 to 8, we would count the number of these that are in that range. So the number is 6 is in that range, 7 is in that range, 9 and 10 are not in that range, right? So the only two that are in this range are 6 and 7. So our empirical approximation of this probability is 2 divided by 7. So that's it. That's all we're doing for the sampling case. So remember, m is the number of samples of this entire sequence, the number of samples of this entire large simulation of flipping n coins. And n is the number of coins we're flipping for each of these simulations. Okay, so now we're going to take another approach, which is the Chebyshev approach. So Chebyshev is one of a number of tail inequalities. Tail inequalities tell you, so if we have some distribution, let's say the mean is here. So they tell you the probability that you're far from the mean is low. So in this case, Chebyshev tells you the probability that you're epsilon away from the mean is at most the variance divided by epsilon squared. So it says that this is epsilon here. So this is epsilon here. So the probability you're in this region here of the distribution is at most inversely proportional to the square of this distance from the mean. Right? So what we're going to do is we'll say that the mean in this case is 5, right? So this is the mean. And so the probability that we're this far away from the mean, that we're in this region 6, 7, 8, is less than or equal to the probability that we're 1 away from 5. So let's look at this another way. Let's use a different color. So the region we're talking about when we're using Chebyshev, let's start off with, we can calculate, this is 6 here, and this is 4 here, and 5 is in the middle, right? So Chebyshev tells us the probability x minus 5 is greater than 1. So the probability x is here or x is here. So x minus 5 greater than 1 is another way of saying x is less than or equal to 4, or x is less than 4, or x is greater than 6. The probability of this happening is at most the variance of x, which we can calculate because we know n and we know p. So we can calculate this exactly. We'll calculate it later. Divided by epsilon squared. So epsilon here is 1, so it's 1 squared. So there we are. So we know that the probability of the number of heads landing in this region is low. As a result, the probability of the number of heads landing between 6 and 8 is even lower because 6 and 8 is included in this region. Right? So 6 and 8 is included in this region. So as a result, this probability is bounded by this probability. And so we can just say that L less than or equal to X less than or equal to U. Yeah. So over here, we're using a greater than. We could have chosen this epsilon. We can just say greater than or equal to. It doesn't really matter. Because this epsilon could have been, it's a very smooth distribution. So this epsilon could have been really close to, we can make it arbitrarily close to 6 and make this arbitrarily close to, we can make epsilon arbitrarily close to 1 from beneath and then make this small. So anyway, so it's basically we can make this greater than or equal to and it's not a problem. Is that right? Yeah, that's right. So we can say this is greater than or equal to, that's fine. And so now all we have left to do is calculate variance. So what have we done? We've said the probability of x, the number of heads coming up in this region, is low. And we've said that by saying the probability of x being in this entire region to the right or to the left is low, right? So variance of x, this is a Bernoulli distribution, so this is binomial, get these mixed up. NP times 1 minus p, and you just know this. So we have n, we have p, we can just compute it. That's pretty much it. So the tricky part is just finding this epsilon here. So this is what you all have to do in code. So there are three scenarios. So let's say the mean is here. If lower and upper overlap with the mean, Chebyshev doesn't help us much. So Chebyshev tells you the probability of being far away from the mean is low. Well, here you're overlapping with the mean, so you can't. Chebyshev just doesn't give you a bound, right? Chebyshev can tell you if the interval were here, further out. Chebyshev can tell you that the probability of being this far out is low because the probability of being out of this region is low. But this is in the region that you're talking about, so you can't really do anything. So in the case that L and U, this interval overlaps with the mean, you can't say much, so you just say the probability is 1. 1 is always an upper bound of the probability. That's a trivial upper bound. You can just say probability is less than or equal to 1, right? So in the case that L and U are above the mean, then this epsilon, you can take it to be L minus mean, right? The distance from the lower end of the interval to the mean. And in the case L and U are below, you can take it to be mu minus the upper, right? So it's just the shortest, it's the end of the interval, the distance from the end of the interval to the mean. Because this is, you want to make this bound as low as possible because you want to say, you want the bound to be as tight as possible. Tight means the bound is as close to the exact computation as possible. So in this case, if we said epsilon is this, let's say epsilon is 1 in this case and it's 3 in this case. Well, this is also correct. So we could use this to get a correct bound, which would say the probability of being outside of this region is small. But that's not going to be as low a bound, so it's not as good a bound. It's not as close to the exact amount, right? So we want to get as tight a bound as possible. So we go, we choose an epsilon that's as large as possible, such that the interval we're talking about is included in the region the bound covers. So the region the bound covers is the area outside of epsilon. So we want to make epsilon as large as possible so that the region that's covered outside of that epsilon includes the interval. So that's pretty much it. Any questions on Piazza, I guess?